Hello students, so continuing our lectures on nanoelectronics, we will first consider, as we have seen in previous lectures, that when we have an quantum dot and two leads as a tunnel junction, there is no direct electrical contact being made between these three entities. So it is as if we can consider that there is a tunnel resistance due to tunneling of current, or we can consider that there is a capacitance like a parallel capacitor. Now this situation can be represented in terms of a Norton equivalent circuit, where we have a tunnel junction which is linked with a parallel combination of a bias resistance and a parasitic resistance, and there is a constant current source, and there is an impedance which is the impedance electrical leads closest to the junction. So this is where we are considering there is an impedance resistance. Now this capacitance C is considered to be much higher than the capacitance that gets created in the parallel plate equivalent parallel plate circuit, and so this value is high. So the reason why this is high, because now we can assume that we have an equivalent voltage circuit, because the time constant of the external circuit is much larger than the time constant for the internal circuit. So this is almost as if the voltage is a constant. Okay, now now this impedance, this is called L stands for the Landauer impedance. I will tell you what is the significance of this. Now there are two cases which may arise, and this L is again a frequency of the time period of oscillations that takes place in the voltage, as mentioned previously. Now there are two cases where that can arise. First of all, when this value is really small, so in that case we can assume that the voltage, this one, is parallel to the tunnel junction. So they are arranged in parallel, and now as electron tunnels, this one is removed across, and there is a quantum effect tunneling, and there is no Coulomb bias existing between them. This is first case. Now in this case, the impedance, this ZL impedance, has got a value of h by 2 square, h by e square. Now this h by e square is called the quantum of resistance. Now not exactly h by e square, h square by 2e. This is called quantum of resistance, and this is the resistance towards a one-dimensional electron transport. And there are two more terms associated with this resistance. That is 1 by nt, where n is the number of conducting channels and t is the probability of transmission. So it is more like the probability that whether the electron will be able to get transmitted or not, rather than the classical resistivity. And this is called the quantum of resistance, and its value is 12.9 kilo ohms if we have considered n is equal to 1, which is the number of conducting channels. If the number of conducting channels increase, the resistance automatically gets halved. So the finite number of conducting channels imposes resistance to this electron flow. Now for high, if the frequency of oscillations again is high, then the lead can be considered to be radiating energy like an antenna, and you can have the impedance as low as 370 ohms. However, if the case is such that this value of this impedance is high, this value is high, so then there is sufficient voltage drop over ZL. Then this indicates that the junction can act like a tunnel junction, because the voltage on this transaction is not fixed because the ZL is high. And so in that case, this the voltage V can oscillate like ACT oscillations mentioned previously.